Imagine a universe so vast it defies comprehension. A universe that, in its infancy, expanded faster than the speed of light. This isn't a fantasy or the plot of a science fiction novel. This is the reality we live in, a reality still shrouded in cosmic mystery. This enigmatic universe, with its billions of galaxies, each home to billions of stars, is still a source of perplexing questions. How did it all begin? What propelled its rapid expansion? These queries lead us to the concept of cosmic inflation, a theory that attempts to explain the universe's early moments. Cosmic inflation posits that a fraction of a second after the Big Bang, the universe expanded exponentially faster than the speed of light. This theory, while not without its controversies, provides a potential explanation for the large-scale structure of the cosmos. Our journey today takes us back to the dawn of time, to the early universe, and the theory of cosmic inflation. In the beginning, there was an explosion. Not an ordinary explosion, but the Big Bang. Picture this: the universe, all of space, time, matter, and energy packed into an infinitesimal point, a singularity. Then, in a fraction of a second, that singularity expanded, and the universe was born. This is the Big Bang theory, the leading explanation of our universe's birth. But the Big Bang wasn't just an explosion, it was a rapid expansion of space itself. In those first moments, the universe was incredibly hot and dense. It was a seething cauldron of fundamental particles, a turbulent soup of energy and matter. Then, as the universe expanded, it cooled. The fundamental particles coalesced into atoms. Hydrogen, helium, and traces of lithium were the first elements to form. These atoms would later become the building blocks of stars, galaxies, and all the structures we see in the universe today. And what about the initial conditions of the universe? The Big Bang theory suggests that the universe began in a state of high uniformity. It was isotropic, meaning it looked the same in all directions, but it was also homogeneous, meaning it had the same properties at every point. This high degree of uniformity is one of the key predictions of the Big Bang theory. But how did our universe reach the immense size we observe today? Enter the theory of cosmic inflation. Cosmic inflation, a theory proposed by physicist Alan Guth, suggests a period of extremely rapid expansion of the universe. A fascinating concept, isn't it? It's like imagining an object growing billions of times larger in just a fraction of a second. Now, let's dive a bit deeper. Picture the universe not as we know it today, but as it was in its infancy, a mere speck of high energy density right after the Big Bang. According to Guth's theory, this tiny universe underwent an inflationary phase, expanding faster than the speed of light almost instantaneously. This expansion was so extreme that it took our universe from being smaller than an atom to about the size of a grapefruit. Incredible. But what triggered this super fast inflation? Guth suggests it was due to a peculiar type of energy field known as the inflation field, with a property called negative pressure. Now, don't let the term scare you. Simply put, this negative pressure created a sort of repulsive gravity, causing the universe to expand at a mind-boggling rate. Why is this theory so important, you might ask? Well, it addresses some of the most significant cosmological puzzles. For instance, why does the universe appear flat and homogeneous? Without inflation, it's hard to explain why distant parts of the universe have the same temperature and density. But if the universe inflated rapidly early on, these regions could have been in close contact before the inflation, explaining their similar properties. Moreover, cosmic inflation also provides a mechanism for the creation of large-scale structures in the universe. You see, tiny quantum fluctuations before inflation could have been stretched during this rapid expansion, becoming the seeds for the formation of galaxies and clusters of galaxies we observe today. Inflation theory proposes an answer to some of the most profound questions about the nature of our universe. It's a fascinating journey into the origins of everything around us, where the laws of physics take on a whole new dimension. But remember, as with all scientific theories, it's our incessant questioning and exploration that brings us closer to understanding the universe's deepest secrets. You might be wondering, is there any evidence supporting this cosmic inflation theory? Absolutely. And let's delve into the two main pieces of evidence, which are the cosmic microwave background radiation and the large-scale structure of the universe. Firstly, the cosmic microwave background radiation, or CMBR, is a relic from the early universe, a snapshot, if you will, of the universe when it was just 300,000 years old. This CMBR is not perfectly uniform. It has tiny temperature fluctuations, or anisotropies, which are crucial to our understanding of the early universe. These anisotropies are the seeds of all current structures in the universe, galaxies, clusters of galaxies, and so on. The pattern of these anisotropies matches the predictions made by the theory of inflation remarkably well. In other words, the cosmic inflation theory precisely predicts the statistical properties of these temperature fluctuations in the CMBR. Secondly, the large-scale structure of the universe also gives us evidence for cosmic inflation. When we look at the universe on the largest scales, we see a cosmic web of galaxies, with vast voids between them. This structure arose from tiny quantum fluctuations in the early universe, which were stretched to cosmic proportions by inflation. The resulting density fluctuations are what led to the formation of galaxies and clusters of galaxies. Once more, the cosmic inflation theory provides an accurate description of the observed large-scale structure of the universe. So, in conclusion, the cosmic microwave background radiation and the large-scale structure of the universe are two key pieces of evidence that support the theory of cosmic inflation. Both of these observations align very well with the predictions made by the theory, lending it robust support. These observations, among others, provide a compelling case for the theory of cosmic inflation. The implications of cosmic inflation are profound, reshaping our understanding of the universe's birth and growth. This extraordinary theory has provided us with a plausible explanation for the homogeneity and isotropy of the universe. These fancy terms simply mean that the universe at large scales looks the same no matter where we look or from where we observe. Isn't that something? In the standard Big Bang model without inflation, it's hard to explain this uniformity. But inflation offers a solution, proposing that the universe underwent an extremely rapid expansion in its early stages, smoothing out any large-scale irregularities. Now let's talk about galaxies, those grand cosmic cities where stars and planets reside. Inflation doesn't only explain the large-scale structure of the universe, but it also has a hand in the formation of galaxies. You see, quantum fluctuations during inflation could have been stretched by the rapid expansion, creating density variations that later served as seeds for galaxy formation. Quite the cosmic gardener, isn't it? Inflation also implies the existence of a multiverse, where our universe is just one of many, each with different physical properties. A mind-boggling thought indeed. Inflation theory, if correct, reveals an extraordinary journey from a universe smaller than an atom to the vast cosmos we observe today. So, what does cosmic inflation tell us about the future of our universe? Well, the fascinating concept of cosmic inflation doesn't just help us understand the universe's past, but it also offers intriguing possibilities for the future. One compelling idea is that of a multiverse, a theoretical collection of multiple universes, including the one we live in. If cosmic inflation is indeed a fundamental property of our universe, it could mean that our universe is just one of many. This eternal inflation suggests that countless universes are being created all the time, each with its own physical laws and properties. But it's not just about other universes. Cosmic inflation could also provide clues about the future of our own universe. It could help us understand how matter will continue to spread and how the universe might eventually end. As we gaze into the night sky, we are left with a thought-provoking question. If our universe once inflated so rapidly, could there be other universes out there waiting to be discovered?